Good day and welcome to part one of our discussion on indefinite integrals. I will motivate this topic by looking back to our previous discussion on the fundamental theorem of calculus, which involves two statements. Part one of the fundamental theorem of calculus tells us that the definite integral from a to x of f of t dt is an antiderivative of f of x. Note what that means as a reminder is that if you differentiate the function, you get back f of x. So this is kind of an ideal scenario. As long as we are integrating from a constant up to x, and x is a variable we are differentiating with respect to, we simply substitute x in for t, and we get back f of x. The second part of the fundamental theorem of calculus gives us a very convenient method for evaluating definite integrals, where the success or failure of being able to utilize this method relies on being able to find this antiderivative big F of that function little f. And let me remind you that in the background of all of this, there is an overlying hypothesis. We do need the function to be continuous on that interval of interest, in this case a to b. Now, both parts of the fundamental theorem of calculus is really related somehow to this idea of antiderivatives. And up to this point, our notation for dealing with antiderivatives has been a bit cumbersome. That is to say, it's not always convenient having to think in terms of little f's and big F's. What the indefinite integral is going to do for us is allow us to have more convenient notation to represent these families of antiderivatives. So the notation where we have the integral f of x dx, so note there are no limits of integration. This is called an indefinite integral of the function f of x, and it represents all possible antiderivatives of f of x. And if you recall back to our language with antiderivatives, that is to say it is the most general antiderivative, which means it includes a plus c. So with indefinite integrals, make sure that you always include a plus c. And it is most definitely worth pointing out that we are doing nothing new in this section. Instead, we're taking this old idea of antidifferentiation, or really the most general possible antiderivative, and we're giving it more convenient, useful notation. For example, if we would like to know the indefinite integral of cosine, we would like to know all possible antiderivatives. So we pick one, sine, and we simply include a plus c with it. Note there is a very big fundamental difference between an indefinite integral and a definite integral, but at the same time they are also very intimately related to each other. So first of all, their differences. An indefinite integral, as we've defined it above, is a family of curves. There is one curve corresponding to each value of the constant c. Whereas a definite integral represents a net difference of enclosed areas and is hence a numeric value. So a definite integral is a number. And a number is very different from a family of curves. But note the relationship between the two, thinking of that second part of the fundamental theorem of calculus. We need to find an antiderivative of f of x, the so-called big F that we see above, but note the indefinite integral certainly can play that role as it represents all possible antiderivatives. We then evaluate it from a to b. So when it comes to evaluating definite integrals, in the background you're finding antiderivatives and hence always finding indefinite integrals as well. The good news is that, as we've mentioned, this is not a new topic. We're taking an old idea and just giving it a new name and some more convenient notation. So we should be able to very easily take our table of common antiderivatives and turn it into a table of common indefinite integrals. So just working down the list. An antiderivative of a constant, as we saw in a previous video, is always that constant times x. And then to make sure we're getting all possible antiderivatives, we always include a plus c with any indefinite integral. An antiderivative of x to the n is 1 over n plus 1 x to the n plus 1. And note, n is not equal to minus 1. Antiderivative of cosine is sine. Antiderivative of sine is minus cosine. Antiderivative of secant squared is tangent. And an antiderivative of secant tangent is secant. So as mentioned previously with antiderivatives, these are all formulas that you should be very familiar with, that you can use and recognize quickly and efficiently. Ideally, you will practice these enough that they just become second nature. A more subtle point I'd like to hit on before moving on to some concrete examples is that an indefinite integral always depends upon an interval. So let me give an example to illustrate this. If you were asked to find the indefinite integral of 1 over x squared, note 1 over x squared is equal to x to the minus 2. So the antiderivative of x to the minus 2 would be 1 over minus 2 plus 1, so minus x raised to the minus 1 power. So minus 1 over x plus c. And if you have any doubts in terms of this formula, you can quickly double check. The derivative of minus 1 over x is the derivative of minus x to the minus 1. The minus comes down front, making it a plus. The new power of x is minus 2. But note, if you look at either of these functions, minus 1 over x or 1 over x squared, they are not defined at 0. So in this case, we would note that we have an antiderivative in any interval staying away from 0. So this could be an antiderivative on minus infinity to 0 or 0 to infinity. So that's just something kind of more in the background. It's a subtler point, but certainly something for us to think about. So let's look at a few examples. Let's find the indefinite integral of x minus 12 sine x. And to get started, note that when we are calculating indefinite integrals, you can break them up over addition, subtraction, and pull out constants. These rules that we get from our discussion on anti-differentiation. So we can break this up into the indefinite integral of x minus 12 times the indefinite integral of sine. Then individually we can take care of each of these. The antiderivative of x is 1/2 x squared. And note, I'm not going to put a plus c here. I need a single plus c to go with my indefinite integral, so I'm going to wait and put that plus c at the end. Minus 12, the antiderivative of sine, switching back and looking at our table, is minus cosine x plus c. So we always get that plus c. And then writing this just a bit more conveniently, we have our indefinite integral. And it's worth noting once again that you all are experts with differentiation. Whereas anti-differentiation or indefinite integrals is a newer topic. So we can always go back and check our antiderivatives with a derivative. And how we check this is we differentiate whatever we come up with for the antiderivative, and we make sure that what we get back is the original function that we were integrating. So the derivative of 1/2 x squared plus 12 cosine x plus c is equal to, where we use what? The power rule in the first term. The derivative of cosine is minus sine, and the derivative of a constant is always 0. So 1/2 times 2 is equal to x, and we're subtracting away 12 sine x. And note, x minus 12 sine x is precisely the function we were integrating to start with, so check, we have correctly evaluated this indefinite integral. So recall there is a very nice connection between an indefinite and a definite integral. For example, now that we've evaluated this indefinite integral, evaluating some associated definite integral is almost just an afterthought. We take our formula from above, the indefinite integral, i.e. an antiderivative, and we evaluate with the fundamental theorem of calculus. So 1/2 x squared plus 12 cosine x plus c is playing that role of big F in the fundamental theorem of calculus. We substitute in that upper limit of integration, 12 in this case, minus sign, and we substitute in 0. And note the relevance of the plus c. It cancels. It's irrelevant. Also, let's see here, 1/2 0 squared is 0, cosine of 0 is 1. So we end up with 12 cosine of 12, not a common value, plus 1/2 the quantity 12 squared minus 12. And we certainly could do a bit more arithmetic, but leaving it in this form as usual is perfectly fine with me. So that completes our introduction into the indefinite integral. What remains is practice. So you'll notice in the note handout there are 3 more examples. What I would like you to do before going on to the next video is to give yourself 10 or 12 minutes and see if you can go through and evaluate those 2 indefinite integrals, and lastly the definite integral. And this is where we will pick up in the next video. So stay tuned and take care.